In this lecture, we're going to familiarize ourselves with the most basic definition of definite integral. And here it is. For a continuous function, must be continuous, on an interval from a to b, the area between the graph of the function and the x-axis between the values of a and b is called a definite integral. And this is a shorthand notation that we use for it. So notice that the integral sign, which is basically a script elongated s, will get the a value at the bottom, so the value that corresponds to the left point of the interval, the b value on the top, the value that corresponds to the right end point of the integral, the function in the middle, followed by this dx that will simply indicate that our function is in terms of x, and we're looking for the area above the x-axis or between the x-axis and the curve, and not, for example, the y-axis itself. Using the definition of the integral as the area, we can calculate integrals of simple functions purely geometrically. So let's see what we can do here. What is this notation asking for? So it's asking for the integral, which is the area under the function and between the x-axis, between 0 and 5, when the function is simply a 3. So let's sketch this out and see what it is that we're given and whether we can compute this area exactly. So I have my function that is equal to 3. There it is. Let's make it a little more straight. It's supposed to be a straight horizontal line right here at 3. And again, my integral is saying that I would like to calculate the area between the graph of this function and the x-axis between values of 0 and 5. So between 0 and 5 here. So I can go up to my function, and the area that I'm interested in is this rectangle right here. Well, this is just a rectangle, so I can easily calculate this area as height times width, and overall get 15. Let's take a look at this next definite integral. I have the area between 0 and 2 of the function y equals x and the x-axis. So here too, I'm going to produce a simple sketch to see if this is an area that I can actually calculate by hand. So my function needs to be y equals x, so this diagonal right here, and I am looking at the area between that and the x-axis between the values of x 0 and 2. So 0 and 2 over here. So if I go up to the function, this is the area that I'm interested in. Now this is a triangle, and I know that the area of the triangle is half base times height, so I just need to figure out what the base and what the height is. The base is clearly 2, and then the height here, well, this function is y equals x. So if this point has a x-coordinate 2, then it also has the y-coordinate of 2. So overall, I have half of base, which is 2, times height, which is also 2. So overall, I actually get a 2. Now notice that these areas are simple enough to calculate if the graph of the function ends up being some kind of a straight line or something that produces areas that I can easily figure out. On the other hand, in the more general cases, like we have seen, for example, with the leaf example last time, that's not going to be possible unless we introduce this idea of infinitely many rectangles that fit under the given curve. So let's unpack this notation a little bit. Again, the integral, as defined, will simply give you the area between the graph of the function and the x-axis. And the notation on the right looks pretty ugly and bulky, but is really exactly what we have done before. So what I have here is the limit as n goes to infinity, which really just states that rectangles are going to be infinitely many of them. We're not going to be interested in any particular number of rectangles, rather we want to have infinity of them. What I have inside is this delta x that stands for the width of each rectangle that is actually going to be a constant once we decide on the number of rectangles. And then I have the function computed at the kth endpoint. So this is going to be the height of each rectangle. And then the summation is going to take the sum over all the rectangles. Recall, in our leaf example, This is exactly what we did. We started off by determining the width. In that case, it was between 0 and 1, and I've divided into n subintervals. So in the leaf example, this value was 1 over n. We then computed the height of the kth rectangle. We summed over all of the rectangles, and once we applied the summation formulas, we were able to take the limit as n went to infinity of that. Now, once again, with examples like the leaf example, be careful that what you're calculating is actually what you want to calculate. Let's recall from 2 lectures ago the fact that the areas, when computed in this way, might end up being negative. And because the definite integral is just a limit as n goes to infinity of the Riemann summation of these rectangles that we built up between the curve and the x-axis, if it happens to be below the x-axis, it will produce a negative area. Therefore, the definite integral by extension also corresponds to signed area, meaning it's positive if it's above the x-axis and it's negative if it's below. So, for example, if here is where I have a 3, then if I were to compute the integral between 0 and 3 of my function, let's call it f of x, then what I will end up having is the negative contribution from the area here and the positive contribution from the area here. If I decide to label areas, let's say A1 and A2, the physical areas that are actually covered, the positive types, then my integral is going to be negating the area underneath the x-axis and adding the area above the x-axis. If you would like to compute the actual physical area covered, so something that, for example, is important in the variety of applications where you don't want to have any area cover negatively and therefore affect the total area calculations, then we're going to have to get a little bit smart with how we apply integrals here. Let's say I label this point in the middle where negative becomes positive as, let's say, b, this break point here. Then, if I would like to actually have both parts count positively, then my integral on this region between 0 and b has to be negated. If I calculate between 0 and b of my function, this has to acquire a negative sign in front of it. The value of the integral itself will be negative because it lies below the x-axis. Therefore, negating the negative will produce a positive outcome. And then I can simply add the area covered from here on. So between b and 3, the integral of my function f of x will produce a positive result and will actually correspond to the positively covered area here. Keep in mind this for a variety of applications. For example, one of the most standard physics applications is the difference between the displacement and the actual distance traveled. Displacement is the difference between the finish position and the start position. However, the distance covered is something that you will have to count positively throughout. If I went out to from my house to the store and back, my displacement is 0, but the distance that I have traveled is of course non-trivial. Therefore, the negative portions will have to be accounted for carefully and separately. Next, what we would have done in class is go over this worksheet. So I actually kept it as a worksheet for your practice, and I'm going to talk a little bit about the examples that are included on it. The first part is just using the definition of the definite integral to get used to the notation. So once again, the notation is saying that the definite integral corresponds to the area between the graph of the given curve and the x-axis, between x equals -5 in this particular case and x equals -3. What you notice in all of these examples is that we have minus x plus 2 as the function of choice for all of them. So what we're going to do is produce a graph of -x plus 2 and then think about how the stated integrals correspond to the area and what that area actually is. So minus x plus 2 will be something like this, intercept of 2, slope of -1. So this is my minus x plus 2, but then I have to calculate it in a variety of different ways. So between -5 and 3, that means that I have not drawn quite enough of the graph. I'm going to calculate it between -5 and -3, which means I have to extend out my function, and the area included there will correspond to this trapezoid. You might know the area of the trapezoid as the formula, or you might want to break it up into an upper triangle and a lower rectangle and calculate it this way. The idea here is to interpret the integral as the area. So we're not using any integration techniques yet. We're working with the integral conceptually. With the graph that I have drawn without modifying it, I can, for example, calculate this integral. The area between the graph of x minus x plus 2 between 0 and 2. So between 0 and 2, I'm covering this area right here. This will be the area of a triangle here. And in fact, I can note that the half base times height will work out to be exactly 2. If I go, for example, between 0 and 5, this is where I'm going to have to start being very, very careful. So if I have a 5, let's say here, I know this is not to scale, then the area, as calculated by the integral, being a signed area, you're going to have to be extra careful with that. If I go between 0 and 5, whatever area lies above the x-axis will be counted positively. Whatever area lies below the x-axis will be counted negatively. So let's carry out these calculations here. So for the first part, for the integral between 0 and 2, my area is positive. So I'm going to have a contribution of 2, because that is the area of this little triangle piece. Between then 2 and 5, the graph lies below the x-axis, so the area of this resulting triangle in the calculations of the definite integral will count negatively. So here I will then have to subtract half of base times height. And what is my base? What is my height? Well, my base is going to be this length, which is 3. And my height is going to be, if I plug in 5 into my function here, minus 5 plus 2 minus 3. But if I've already accounted for it being negative, my minus is already included. So these are going to be my total calculations here. Between 0 and 10, you're going to carry through something very similarly. Between 0 and c, you're going to have to think about how does the placement of c affect whether or not there's any negative area to account for or not at all. Okay, this example is fairly geometric. Please go through it. There's a few more examples like that on WebWork. These are really great examples to develop conceptual understanding of definite integrals as areas, which is going to be incredibly important for a variety of applications. Let's take a look at this next question here. Here, all we have of a function is its graph. We don't have a formula. We have no analytic way to work with it. So let's go through a few examples here. We're going to use the definition of the definite integral as the signed area, again, I cannot emphasize this enough, to compute the following integrals. Let's see what we can do. If I would like to compute the integral between 0 and 1, that means I'm computing the signed area between the function that I'm given and the x-axis between 0 and 1. So here I have 5, so 1 will be right here. So I am computing this little area right here. It's a little triangle, and I can see that the total area there will be 1/2. It's on the positive side of the x-axis, so it's definitely positive. Between 0 and 2, it's like I am starting at 0 and I am sliding my paint roller to the right. So between 0 and 1, I've managed to cover this much area. Between 0 and 2, I continue on, and now I've covered this much area. You can again compute it in different ways. You can think of this area, for example, as just the area of a triangle, or you can see that this is 1 square and 2 half squares, which altogether will give you the area of 2. Between 0 and 4, now we're going to go up to here with our paint roller and cover up this entire area. And you can use your previous calculations to help you along. I can see that this entire area is the area that I've computed between 0 and 2, plus the area of this new square. So it's going to be 2 plus 4, or overall 6. So far, we have not encountered any negatives. Between 0 and 6, so 0 and 6, this point right here, I have the area of this trapezoid. And again, I can actually utilize all of my previous calculations, or I can also notice that I can break up this area into pieces where this piece has the area of 4, and these two pieces together form another one of these squares. So overall, my total area will be 8. Now, the next one is where it gets more interesting. 0 to 8. So 5, 6, 7, 8. Now I have to count the area covered between 0 and 8. We notice that this area will be counted positively, whereas this area will be counted negatively. And we're going to have to make sure that this is taken care of. We notice that we have just counted the area between 0 and 6 to be 8. So I can say that this area is going to be 8 minus whatever happened between 6 and 8. So minus this little bit, which is a little triangle whose area I can count easily, and I can see that it's equal to 2. The other way that you can consider this area, for example, let me actually shade this to show you the pattern, is that this negative triangle will cancel out with this, for example, positive triangle. These two are going to be the same, which means that I'm going to have a positive contribution equal to the area of this piece that I already actually know to be 6. So this is another way to double check your answer and to make sure that it's the same. Similar logic can be applied to the integral between 0 and 10. I will leave the calculations there to you. You should end up getting, I believe, 2. Let's take a look at a few more general questions about the structure of the pattern on this graph's particular areas and definite integrals. For what value or values of x is the integral between 0 and x of my function equal to 0? This really gets at the bottom of what it means to have a definite integral. So the integral between 0 and x means I am looking for the area between the curve of f of x and the x-axis, and the question is asking, if I start at 0, so I kind of start my paint roller here and I move forward, at which points will I have covered the area equal to 0? Where do I have to stop so that my total area covered is equal to 0? Well, first of all, if I start right here and I don't move at all, then of course the area covered is going to be 0. So one of such x values is 0 itself. What about the next one? So if I go from here and I move to the right, for now, as we've noticed in part 1 of this question, all I'm doing is acquiring positive area, so I can not get at 0. But then after 6, I start accumulating negative area. So the question really becomes, when is my negative area going to cancel out all the positive area contributions here? And I can see that, for example, when I got to 10, my total was already only 2 and decreasing, right? After I hit this point, I'm covering negative area. So whatever positives have happened before are being decreased all the way to 0 and then likely into the negative if the graph continues in this manner. By the time I got to 10, I only had 2 units of positive area. So I can see that by the time I get to 11, I would have canceled my area completely. Okay, so let me go through this again, sort of knowing the answer. Let's say I stop at 11 here. What I am claiming is that the area covered between 0 and 11 is now equal to 0. The positive area here and the negative area here are exactly the same. Notice that the shapes are not the same, but the areas that they cover are actually the same. Let's take a look at this next question. For what values of x is the integral between 0 and x negative? So again, we have to think of what the integral means in terms of area. This is asking for what value or values of x is this integral, this area between the function and the x-axis, negative. So again, think of the paint roller. I start at 0 and I start painting. So far, I'm just acquiring positive area because it's above the x-axis. After 6, I start acquiring negative areas. Now, if I stop somewhere right here, I still have more positive than negative. So in order for my total area to be negative, I have to keep going. We have determined that at 11 is where I have area equal to 0. So this is when the top and the bottom are completely balanced, which means that if I continue going forward this way, I will be acquiring more negative area and no positives. So from this point on, all I'm accumulating is negative area, and therefore the value of the integral is going to be negative. So here, I'm not going to have a single value of x. I'm going to have any x greater than 11 will in fact produce a negative area. Because my integral is counting from 0 on, once I'm past 11, the area is going to be negative. Let's take a look at the last few here. I'm going to do just h and leave the last exercise for you to complete. Give an example of values a and b such that the integral between a and b is equal to 2. So again, the definite integral means the area between the graph of the function and the x-axis. And I want that area to be equal to 2. So all I have to do is find a chunk on the graph where I can read off the values of a and b so that the area enclosed in between them, between the graph and the x-axis, is actually equal to 2. Now I can cheat a little bit and notice that, for example, one of the integrals here was equal to 2, so I can simply take that as my example. The integral between 0 and 2 is equal to 2. So if I go from here all the way to 2, then the area covered is going to equal to 2. If I want to be a little bit more adventurous, let me pick something that we haven't seen yet. I can, for example, claim that the area between 2 and 3 is also equal to 2, because the area covered between 2 and 3 is under the curve is going to be just that, right here. In fact, I can also see that the area between 3 and 4 is going to be 2, and so I have lots of options here. So for example, I can say that a can be 0 and b can be 2, as per my cheating example, or I can have that a is equal to 2 and b is equal to 3, or there's lots of other options. See how many options you can come up with for the integral in the last part.